Hello everyone, I'm Heejun Moon in High Vision Lab, Hanyang University. I'm glad to share our recent research titled Efficient Privacy Preserving Visual Localization Using 3D Ray Clouds. In this part, I'm going to briefly introduce privacy preserving visual localization and its related works. In server client-based visual localization systems, clients download the 3D point map data from the server and estimate camera pose with given image. However, in this scenario, if the malicious attacker gets access to client and 3D point map, scene detailed images can be reconstructed from projected 3D points with inverse SF network. This raises privacy concerns known as inversion attack when recovered images include private content. To address the privacy concern, Special et al. Proposed a new 3D representation called line cloud. Each 3D point is replaced by a 3D line passing through it, where direction of line is drawn from a uniform distribution on the unit sphere. This prevents the inversion attack while allowing localization with P6L minimal server. As the motivation of our work, the first is to neutralize line-to-point method recently proposed by Chalani et al. They presented the method to recover 3D point cloud from 3D uniform line cloud based on the empirical found that in 3D random lines, the closest point to neighboring lines can be good candidates of original point. This raises the privacy concerns again with line clouds, and our motivation starts from lifting into 3D lines, which is robust to line cloud inversion attack. Next, our motivation is also derived from slow runtime in single image based localization. As P6L minimal server originated from generalized 6-point relative server, it also suffers from a higher algorithmic complexity as well. Hence, achieving real-time performance with P6L is challenging and requires multiple images as input. With our two major motivations, we thought that lifting into 3D lines intersecting at a particular point could be a promising approach. First, line-to-point methods yields trivial solutions, as estimated closest point to neighbor lines are always located at the intersection point. Next, we can regard the intersection point as a virtual camera center. This enables to cast the generalized relative problem into classical relative problem where efficient 5-point server can be utilized. However, as 5-point server has scale ambiguity in translation, we instead utilized additional intersection point to estimate translation scale. Now, we introduce our new line lifting method called 3D rate clouds. Constructing rate clouds involves the simple following steps. First, the two ray centers are set with k-means clustering. Then, each 3D point is randomly assigned to the two ray centers. Finally, 3D lines that pass 3D points and their corresponding centers are drawn. K-means clustering was adapted for setting ray centers as it can avoid two extreme cases, inducing degradation in localization accuracy. For localization, RayCloud leverages efficient 5 plus 1 solver, achieving real-time performance in single image-based localization. Compared to line lifting approach using Pixel server, RayCloud showed significant improvement in runtime with two public datasets. For robust pose estimation, we minimize epipolar distance-based cost with nonlinear optimization. As briefly mentioned before, knife line point method recovers only two ray centers. As 3D lines intersect at the ray center, the closest point to neighbor lines and estimate peak are always located at the ray center. The reconstructed image from this trivial recovery shows meaningless contents. However, we thought that by only considering 3D lines from the opposite ray center in neighbor line estimation, the contribution of 3D lines sharing the same ray center vanish. The recovered 3D points and images show improved quality, confirming our intuition. We also reject rays closely aligned to the baseline that connect two ray centers. By rejecting the smallest beta percent of lines in ascending order of their angle with the baseline, we empirically found that ray rejection helps to improve recovered 3D points and image quality, yielding corner cases. To prevent these cases, we propose a voxel-based ray sampling where 3D points in each voxel grid are assigned to the same ray center. This can discourage lines lifted from the closest point being included in neighbor line estimation, thereby degrading reconstruction quality. We also adapt 3D checkerboard pattern to yield rays uniformly distributed, allowing stable localization. The quantitative result with two public datasets show that ray cloud approaches can achieve real-time performance without significant degradation in localization accuracy. Also, proposed voxel-based ray cloud shows the worst 3D points recovery and reconstructed image quality, indicating the best privacy-preserving performance. The trade-off curve plotting localizing performance and reconstruct image quality along the different density levels show that ray cloud-based approach can preserve privacy without heavily compromising localizing performance and show significant reduced runtime. The qualitative results of 3D points recovered with lined point method confirm that the ray cloud approach yields unrecognizable results, even though our modified lined point method was applied. The reconstructed image of ray cloud and voxel-based ray cloud are also concealing scene details due to bad recovery of 3D points. In conclusion, our research presents an efficient privacy-preserving framework based on a new line lifting approach called 3D ray clouds, showing real-time performance in single image-based localization while maintaining privacy-preserving capability. We propose customized line-to-point method yielding corner cases for ray clouds and its effective defense mechanism based on voxel grid. We also experimentally demonstrated the effectiveness of ray cloud with two public datasets. Thank you for watching.